Hey there, folks. We're back. Oh, and I'm sorry, this procedural thing, let me take care. Okay. Let's go over the homework problems. Yeah, I have to tell you, I really enjoyed the way the homework went today with the document camera in there. Everyone seemed to adjust to that quite naturally. And we moved quite quickly through the homework problems, which I thought was great. I think it works good that you guys are explaining the problems yourselves. So yeah, I'm really pleased with how that went. The other side of some of the changes we're doing is that instead of me just posting completed homework problems, I'm going to work through them with you. And so let's start now with problem 2A in 3.1. Yeah, I think I posted 3.2, but it's actually 3.1. So okay. Let's let. I'm questioning myself. I'm pretty sure it's 3.1. Hold on. Yeah, 3.1. Good. Yep. Okay. So I'll fix that in the title. Problem 1 says, okay, you got these non-zero integers, a, b, and c. Prove that if a divides b and a divides c, then a squared divides bc. So the proof of that would go something like this. Since a divides b, then there exists some integer m such that b equals a times m. And then we do the same thing with c. Since a divides c, then there exists, I don't know, n. Such that c is equal to a times n. Alright, so we want to look at a squared. Well, I'm sorry, we want to look at b times c, excuse me. So just this is b, this is c, then bc is am times an, which is a squared mn. So since mn is an integer, then a squared divides bc. That's it. So I had to show. Okay. 2b is actually very, very similar. If we're going to say this, if a divides b, then there exists an m integer such that b is equal to am. Since d divides c, oops, forgot my little backwards e, so it's right there, exists a n integer such that c is equal to dn. And now we're actually looking at bc again, right? am times dn, and I want to pull out the AD there. So since mn is an integer, then AD divides BC. Okay. Actually, if you think about it, if we had this proof in place first, I could have proved this one using this one, right? Let D be A. I got it. That's it. It's done. Yeah. So, okay. There's the first couple parts of, no, I think B just had, 2 just had those 2 parts, so we're good there. 3 says provide a proof or counterexample. Here's some non-zero integers, and if A divides B times C, then it has to divide either B or C. Well, I think I can get you a counterexample to this one. We got to be a little careful anytime we go down from a bigger number to dividing smaller numbers. I think my counterexample on this one, and there's several, so yours may be different, but I think I did something like 6, right? 6 divides 3 times 2, which is 6, but 6 does not divide 3, and 6 does not divide 2. So that's a false statement in general. Okay. D and N non-zero integers, prove or disprove. If D divides N squared, then it has to divide N. Well, again, anytime you're going from a big number to a smaller number, you got to be careful. My counterexample on this one, and there are several, was 12 divides 6 squared, which is 36, but 12 does not divide 6. 6 divides 12, but not that way. Okay? All right. Problem 5 is, okay, we've got A, B, and C natural numbers show that if A divides B and C is less than A, then A cannot divide B plus C. Now this one we have to be a little careful because we don't have a good way of representing does not divide, right? What I'm going to do in this case is actually kind of prove the contrapositive. I'm going to say, okay, let's let this part be true, and then show that if this doesn't happen, in other words, if A does divide B plus C, then C has to be bigger than or equal to A. Okay? So let's start off by letting A divide B. Okay? And what that means for us is then there's some kind of integer N out there such that B is equal to A times N. Okay? So then let's suppose, and this is in, remember I'm working towards the contrapositive here. So I'm going to suppose that A does divide B plus C. Okay? Oh, and I should have said something here. This is kind of an important part. Just to be accurate on this, these are natural numbers. So I don't have to worry about B being negative, A being negative. I could actually choose my N here as a natural number, which is fine. It's a subset of the natural numbers are a subset of the integers, so that's fine. It becomes a little important here because we don't want to have to deal with negatives throughout this. So, okay. So anyway, then there exists M, I don't know. And again, I can stick with the natural numbers on this, such that B plus C is A times the M. Okay. Now, since this is where the natural number business comes into play, since C is 1 or bigger, it's a natural number, then I've got B is equal to AN, I've got B plus C is equal to AM. That tells me that this and C is 1 or bigger. So M has to be bigger than it. Okay, and that's kind of important later on. All right, then let's look at what happens with C. So then I've got this and I've got B up here. So then AN, this is my B, plus C equals AM. And that means then that C is equal to AM minus AN, or A times M minus N quantity. Okay? Since M minus N is bigger than 0, right? And that comes from this. It's got to be at least 1, right? And it could be bigger. So C is going to be some either 1 times A or 2 times A or 3 times A or whatever it is. But that then gives us that C then is bigger than or equal to A. Okay? Therefore, and this is where we kind of wrap it up, so what we've proven here is that if this happens, then this happens. I'm sorry, if this doesn't happen, this doesn't happen. So the contraposit is true. If C is less than A, then A does not divide B plus C. There you go. Okay, just a different way of going about it. Problem 6 had us looking at the connection between these sets, Dn and M sub n. Dn is the set of all divisors of n. So if n is a non-zero integer, D sub n is all things that divide n, all x that divide n. And M sub n would be all multiples of n. So in our problems here, we're going to let A and B be non-zero integers so we can use them in that D and M notation. And so in problem A here, we want to prove that if A divides B, that A divides B if and only if the set of divisors of A is a subset of the set of divisors of B. So I think this is fairly straightforward. We let, my proof, let's let A divide B. Okay, then what does that mean to us? And there's some kind of integer n out there such that B is A times that n. Now with that assumption, I want to take something. Remember how we do set inclusion? We take something out of this set and show that it's in that set. Let X be an element of D sub A. And that means that X is a divisor of A, divides A. Then there exists, and I got to have something besides N. How about M? Such that A is X times the M. Okay. Now, what I want to show is that X has to be a divisor of B as well. So I think I go straight into this formula right here. Then B is equal to and A is x m, and then I've got an n right there. I can certainly group those together. And then since mn is an integer, then x divides b, and that means that x is a element of dB. Thus dA is a subset of dB. Okay, and we are halfway there. Actually, we're over halfway there because it gets way easier if you go the other way. Let dA be a subset of dB. Well, A is since A divides A, then A is in dB, and then since this is a subset of that, A is in the set of divisor to B, and what that means then is that A divides B. Done. Oops, I should have put my closing therefore the statement's true. Okay. And then leave my box there. Okay. Not too bad, right? And actually the proof for B goes right along those same lines. If we're going to prove that A divides B implies that M sub A contains M sub B, it's pretty much the same. Okay, slight directional things, but nothing bad. So let's start with the left-hand side. Let's let A be B, divide B. Then let's see if we can draw the parallels. Then there exists n integer such that B equals an, okay? And now I'm going to let my x be in this, right? I want to show set inclusion. So let x be an element of mb, okay? Then that means x is a multiple of b. And I should have said it. I typically do this. Then there exists, and I'll lowercase m, such that x is m times b. Okay. But now, what I want to show is that this x is a multiple of a. So I've got a formula for b here. I think before I put this up into there. This time I'll put this down into here. Then x is equal to an times the m, or a times m times n. Since mn is an integer, then that means that x is a multiple of a, so it's right in this set. Thus, mb, is a subset of ma, which is the same thing as we wrote up here. Okay. Again, I think going the other way gets quicker. Let m sub a be a subset of m sub b. Since b is a multiple of itself, I'm sorry, let me say it right. Since yeah, that's right. I got it right. Since b is a, did I say it backwards? I did say it backwards. That's why it was confusing me. Sorry. That was really throwing me. Since B is an element of MB, it's really a multiple of itself, then B is an element of MA, then there exists some, I don't know, use some different K integer such that B is A times that K. Well, what that really means then is that A divides B. Therefore, statement holds. Okay? All right. C and D, many of you kind of pulled on this theorem out of this corollary out of the book, or theorem out of the book. Let me kind of get just a little scratch paper here that basically said that if A divides B and B divides A, then A is a plus or minus B, or that. That means exactly the same thing. And the way they showed this is by you can see the proof is quite nice. They say if A divides B, then you've got A is then you've got B is I think they use U and D for some reason. I'll use A and M, and then here A is B and N, for some integers M and N. And then they substitute in, B then is B M N, which means that M N is 1. So this kind of means that M is either a plus or minus no, I'm sorry. That's not what it means at all. It either M and N are both 1, in which case A and B are equal, or M and N are both -1, which means they're the opposites, right? Right. So that was the proof given in the book. This is kind of like option 1. You could certainly do this. Option 2 is the way I'm going to show it to you, and that is to actually show that D of A, the D of N, is equal to D of a negative N. So, and that's kind of the way I would start. Note that D of N, for a general N, is equal to D of negative N. Okay, to prove that, let X be an element of D sub N. Here's my little proof. Okay. Then X divides N. There exists a K integer such that N is X times the K. Alright. Then negative N is a negative XK, and that means negative N is X times a negative K. Since negative K is an integer, then X divides negative N. Okay. And then, so d of n is a subset of d negative n. Okay, and then the same proof for d negative n gives us d of n equals d negative n. It is the same proof, actually, so there's no change there. So, okay, if this happens, then A is equal to a plus or minus B. So really two cases. If A is equal to B, then we have no problem saying dA is equal to dB. If A is equal to a negative B, then dA equals D minus B, which equals dB, using our little corollary there. Okay. So now let's go the other way. dA equal dB. Okay. Since the absolute value of A is inside of dA, then the absolute value of A is in dB. So the absolute value of A divides B, and that means that the absolute value of A is less than or equal to the absolute value of B. It can't be greater in magnitude than the B. Okay? And so I think you know where I'm going with this. Also, since the absolute value of B is in the divisors of B, and the absolute value of B is in the divisors of A because they're equal. So the absolute value of B is a divisor of A. And that means the absolute value of B is less than or equal to the absolute value of A. The magnitude has to be less than A. So if that's less than or equal to this is less than or equal to that, then they're equal. Nope, not quite. Then, therefore, the statement holds. Okay. I don't know if that's easier or simpler than the option 1 route or not, but it's kind of the way I did it, and it's a different way of doing it, so I'm just giving you a heads up. You can do it different ways. To do the same thing with the multiples, I would kind of go the same route. Note that, or I did. I mean, you can go the option 1 route, but still, note that m of n is equal to m of a negative n. Let x be something in multiples of n. Then there exists a k integer such that x is n times k. Then x is also equal to that. So since now negative k is an integer, Sorry. Then x is a multiple of negative n, and x belongs inside of m negative n. So you've got m of n is a subset of m of a negative n. The same proof shows multiple of negative n, subset of multiple of n. Thus, m of n equals m of a negative n. Okay? So now, let's go to our proof. Let's let absolute value of a equals absolute value of b. Then a is a plus or minus b. If they're equal, we have nothing really to show. If a equals a negative b, then m of a equals m of a negative b, which is m of b. Okay. Now let's go the other way. If m of a equals m of b, okay, now I think you got to step in and do some stuff here, since the absolute value of a is a multiple of a, then a is going to be an MB. Thus, B divides the absolute value of A. That's what we mean by this, right? That this is going to be divisible by the B. So the absolute value of B then is less than or equal to the absolute value of A. Since absolute value of B is in B, you see where I'm going, then absolute value of B is in the multiples of A. Thus, A divides absolute value of B, and the magnitude of A then has to be less than or equal to the magnitude of B. Since you have both, then they're equal. Therefore, okay. So I don't know if that's maybe it's more work than the option one that Marcus and a few guys took, the theorem 3.1.7 or whatever that was, but still not too bad. Okay, so problem 10 says that we've got a prime that's greater than 3. I think Lauren did this one, did a great job with it. We need to probably point out where this comes into play, the greater than 3 business. Then show the remainder when P is divided by 6 is either 1 or 5. Okay. So the proof of this is really, it comes out of that division algorithm, which is kind of a common sense thing, but still. We know that this prime can be written as 6 times a quotient plus a remainder where the remainder is I think I wrote it like this: 0 to 5. Okay. It's important to note that if since the prime is greater than 3, then it can't be 4. It has to be at least 5. So okay. I just point that out because it makes all the remainders here then possible. You know, if P is 5, then the quotient is 0 and R would be 5, right? So what follows here is just a series of knocking out the other ones, the 0, the 2, the 3, the 4. Okay. Suppose that R is 0. Then we have P is equal to 6Q, which is 2 times 3Q. Thus, and it's because 3Q is a well, I guess I can just say this up here, Q and R integers. Right. This means, though, that 2 divides P, which is a contradiction. Suppose that R equals 2. Then P equals 6Q plus 2. I think you see where we're going with this. This is 2 times 3Q plus 1. Technically here you need to say since 3Q plus 1 is an integer. I didn't say it the first time. Then 2 divides P. Contradiction. Let's do it again. Suppose R equals 3. Then P is 6Q plus 3, which is 3 times 2Q plus 1. Since 2Q plus 1 is an integer, then 3 divides P, which is a contradiction. Okay, we're getting there. Last one, suppose R is 4. I'll put over here, then P is equal to 6Q plus 4, which is 2 times 3Q plus 2. And then again, since 3Q plus 2 is an integer, then 2 divides P. A contradiction. Remember, P is prime. Therefore, by really the process of elimination, the only possible values for R are 1 and 5. Okay? Not too bad. I mean, we just had to knock out all the cases that wouldn't work. Okay. Problem 12, we've got A and B are non-zero integers. We suppose here that S times A plus T times B is 1 for some integers S and T. show that A and B are relatively prime. The really relative prime means they have no common prime, and that's kind of hard for us to show sometimes. It might be easier to do this by contradiction. Say, well, suppose they aren't relatively prime, and then show that if this holds, something crazy happens. Okay. All right. So that's going to be the route that I take on this. Suppose, and I'm using suppose here because I'm doing a contradiction proof. That's kind of my code word for contradiction proof. Suppose that A and B share a common prime P. Then P divides A and P divides B. Then there exists, and we've pulled this stunt before, M and N, okay, such that A is P times M and B is P times N. Then let's go into this. This is where things get a little wild. Then S times PM plus T times Pn equals 1. And now note, this is not a chain of inequalities. This is an equation. Okay, so this is a situation where I could, if I wanted to, pull things from one side to the other. I've really stressed with you guys the difference between here's an expression which is equivalent to this expression, which is equivalent to this expression, which is equivalent to this one. That's a chain of equalities, and we just have to take what's here, juke it, take what into this, take this, juke it into what's this. But with equations, they just give you equivalent equations. Okay, then now I'm not going to juke things from one side to the other, but I am going to factor out this P plus Tn equals 1. Okay, but if P is a prime, it's 2, 3, 5, whatever it is, and this is an integer, which it has to be an integer. There's no way you can multiply and get 1. Since P is prime and Sm plus Tn is an integer, this is a contradiction. Thus, A and B are relatively prime. Okay. All right. Getting closer. I think we went up through. I think we got to 19. So let's take a look at 17. 17 really wasn't that bad. We're told A and B are natural numbers that leave a remainder of 2 when divided by 7. And we want to show in the first part that 7 divides the difference. Okay. Okay, so here's the way I would do that. From our given and the division algorithm, I guess I need colon there, comma. There exist a couple different quotients. The remainder is given to us. The quotients, we don't know what they are. So maybe I'll call them Q sub A and Q sub B. The quotient that goes with A and the quotient that goes with B. Such that A is 7QA plus 2. The remainder is given. And B is 7 times the quotient for b plus 2, the remainder's given. Then what I want to look at is a minus b, which just substitute these things in. This is now 7qa plus 2 minus 7q sub b plus 2, which when you distribute that through there, you get 7qa minus 7qb. The plus 2 and the minus 2 are gone. And this is 7qa minus qb quantity. Okay? Which is pretty much all we have to show to get this divisibility, right? Since qa minus qb is an integer, then 7 divides a minus b. Okay. The b part of this had us showing that that if we look at now 10a, that we'll have a remainder of 6 when we divide by 7. Okay. So again, I would point out from our given information and the division algorithm, there exists a q such that a is 7 times this q plus a remainder of 2 that was given to us. Okay. Then 10a would be 10 times this 7q. I meant to put my 2 in there, plus 2. So this is actually, it's 70, but I'm not going to multiply that out. I'm going to say 7 times 10q. Just swap them out. And I do have 20 over here. But I can pull out a 14, and that'll take care of it, right? This is 7 times 10q plus 14 plus 6. Very important, that's 6. So this is 7 times 10q plus 2 plus 6. Okay. And that's all you have to show. Here you go. There's your remainder. It's in the right range. It's bigger than 0, less than 7. So, thus, the remainder is a 6. And they ask us here about 100a. Well, let's avoid the formal proof stuff and just kind of talk it out. 100a, using the same kind of stuff I did up here, 100 times 7q plus 2. Oh, yeah. A is right, 7q plus 2, right. So this is 7 times 100q, and then 200, and I think isn't 1, let's see, divisible by 7, so 1454. No, 7, 4, 56, yeah, there we go. So 196 is what I can pull out of that. Okay, and so that is 7 times 100q, and I think that's 28 plus 4. So your remainder is 4. Okay, so I think you see where we're going there. These kind of problems are actually going to help you a bit with the homework for Thursday. And then the last problem here is to prove that 3 divides the quantity nq plus 2n for all natural number n. And I'll be honest, because we're dealing with a countable set, it made sense to me. You know, I started plugging in numbers to see if I believed it. And I thought, oh, I think that I can actually, you know, do this using induction. So I'm going to proceed at this via induction. So I would start out by saying, note that 1 cubed plus 2 times 1, which 1 is our first natural number, right? So this is 1 plus 2 equals 3. And 3 divides 3. So the initial step holds. Now let 3 divide k cubed plus 2k for some natural number k, and let's consider k plus 1 cubed plus 2 k plus 1. Okay. First, I would point out that there exists some kind of integer. I don't want to use n. I can use m. Is that okay? M such that k cubed plus 2k is 3 times m. Okay, that'll become important later on. Now, k plus 1 cubed plus 2k plus 1. Alright, this is k cubed plus 3k squared plus 3k plus 1 plus 2k plus 2. So let's be careful here and pull out this business. I've got k cubed plus 2k. Alright, that's here and here. And then what am I left with? 3k squared plus 3k, plus 3. Dandy. So from above, this is 3m. And the important part of this is you note that there's a big old fat old 3 hanging out right there that we can just factor out. Since m plus k squared plus k plus 1 is an integer, then 3 divides the k plus 1 cubed, plus 2k plus 1. Thus, remember our closing sentence here, the inductive step holds. Meaning that for any k I do this at, I've now shown I can do it for the next number. So I go back to my 1, and that works for 2, 2 works for 3, it works for then 4, then that works for 5, and so on. That's the way induction works. So therefore, by induction, the statement holds. Okay, and actually I think it was, I forgot who did, Ryan maybe, did a really nice job. If I got the wrong person, forgive me. But whoever did a really nice job of actually kind of presenting that very proof at the board. Okay, we will pick up then after this. I think we've got a couple more, 20 and 21, I think it is, something like that. We'll pick up there on Thursday and then start doing the things out of the divisibility test. All right, we'll see you